In this video, we're going to have a look at how direct proportion can be combined with differential equations, and we're also going to deal with logarithms a little later on in the question, parts B to D, in fact. It tells you the rate of change of temperature. Well, the rate of change of anything is how it changes with respect to time. And it tells you that the temperature of the kettle and the water is represented by y. So we can straight away form an expression dy by dt. This is what represents the rate of change of temperature in this question. It tells you that it's directly proportional to the difference between the temperature of the water in the kettle, which is y, and the room temperature, which is 20. So the difference between y and 20 is, well, y minus 20. And you can pretty much assume that the temperature of the kettle in the water, because it's heating up, it will be larger than 20 degrees. We've almost reached a differential equation for this equation, but the thing is, for the relationship, with this here, you can always replace this with an equals constant. So from here, you can say dy by dt equals a constant multiplied by y minus 20, and that will be a differential equation on part A of this question. Moving on to part B of this question, how you can show that y is equal to ae to the power of kt. From this expression here, this is when differential equations comes into play. So just a reminder, you take all the terms with y to one side, and all the terms that don't have y, you sort of keep it on the other side. In this case, let's divide both sides by y minus 20. So we have 1 over y minus 20 dy by dt is all equal to a constant. And then multiply both sides by dt to get that 1 over y minus 20 dy is all equal to k dt. You might ask, that's a dt. You might ask, why don't I just take the constant to the left-hand side? If you spot in the answer, there's a power of kt. The only reason you can get to that, or the only way you can get to that, is when you integrate this, because when you integrate a constant with respect to t, that's what will get you to kt. So that's why I kept the k on the right hand side. I'd always say compare to the left and actual answer, because it'll help you realize what you want to keep on what side. Once you reach this position here, there's a rule that when the numerator is a differential of the denominator and you're integrating the whole fraction, it's equal to ln of the denominator. In this instance, when you differentiate y minus 20, it's 1. So this whole integral is ln of the denominator, ln of y minus 20. And we can say that's equal to the integral of k with respect to t, which is kt, and then all plus c. Okay, so we reached this position, but how do we reach this position now? Well, to get rid of the ln, we apply the power of e to both sides of the equation. That's because e cancels out with the power of ln, leaving you with just what's inside of the bracket, which is y minus 20, and that's equal to e to the power of kt plus c. Once again, comparing it to the answer, we realize that the 20 is on the other side, so let's add 20 to both sides of the equation, and that'll get you to y equals 20 plus e to the power of kt plus c. Pretty much got the answer now, but instead of e to the power of c, there's a term of a. So you can say something like, let a equals e to the power of c. Because of how indices work, we can separate e to the power of kt plus c into e to the power of kt multiplied by e to the power of c. And then you can replace e to the c with a. So it's going to be y equals 20 plus a e to the kt. And that's your final answer for part B of this question. Perfect. Let's now move on to part C of the question. So I'm going to change the pen color actually. I think it might also be best if we don't need any of this information, so I'm going to rub it out just so you guys can see the question while I'm doing part C. So in part C, it tells you that the initial temperature is 100 degrees. That means that when the time is 0, when t equals 0, the temperature y is equal to 100 degrees. And we can use that to find the value of the constant a. So let's do that. Replacing y with 100 in this equation is equal to 20 plus a multiplied by e to the power of kt. And because you're doing k times 0 is e to the power of 0, and all of this is just equal to 1. That means that 100 is equal to 20 plus a, in which case we subtract 20 from both sides and we get a is equal to 80. Once you've got the value of a, you can then write the equation out as y equals 20 plus 80 e to the power of kt. And I'm sure that'll help for part D of the question. Yeah, actually it will, because it tells you that after 8 minutes, so because t is the time in minutes, we can substitute in the fact that when t equals 8, the temperature is 60, so y is equal to 60. Let's substitute that in. So we have 60 is equal to 20 plus 80, multiplied by e to the power of k, which we're trying to find, multiplied by t, which is 8. So let's write a power of 8k. We start by subtracting 20 from both sides, so 40 is equal to 80 e to the 8k. You then want to divide both sides by 80. 40 divided by 80 is just a half, is equal to e to the 8k. You don't want to apply the ln to both sides. Ln of a half is equal to 8k. And once again, I always like to just look at the answer to see what you want to get to. Well, how can we go from ln a half to ln 2 somehow? Well, a half is the same as 2 to the power of minus 1. On top of that, we can get the minus in front of the ln function by using the fact that where there's a power, you can take that forward as a coefficient. And you can make that equal to 8k. You then divide both sides by 8 to get minus 1/8 of ln 2 is actually just equal to k. And that's your final answer for part D of the question. Pretty difficult question, but hopefully that made sense to you guys. If you enjoyed the video, be sure to like it and subscribe. I'll post more content like this very soon. Check out my playlist, by the way, of more videos on differential equations and exponentials.